Imagine you wanted to do a task like draw a painting or solve an equation, but the task gets too complicated and you give up. The next best thing you can do is approximate. In maths and science, we do the same thing. That is, if solving a problem gets too difficult, we try and approximate the answer. We do the same thing by approximating a function using its Taylor polynomial or Taylor series. But before we go there, you need to understand what a derivative is. Derivatives basically give us information about how a function changes near a point. Imagine this curve represents the distance traveled by the car in 10 minutes. Follow 2 points on this curve and draw a line through these points. The steepness of this line should give us the rise over run, or the difference in distance divided by the difference in time, which is the velocity of the car. Now the actual derivative is what this ratio approaches as we bring the 2 points closer and closer and closer. What all this means is that the derivative gives us the rate of change, and the steepness of this line shows us how sensitive a point is to change. That is, if the steepness is high, then the point is more sensitive to change as compared to when the steepness is low, where the point is less sensitive to change. Now we took the derivative or the rate of change of distance and we got the velocity of the car. Similarly, we can take the rate of change of velocity to get the acceleration of the car. It can also be viewed as taking one more derivative or taking a second derivative of distance, which is represented like this. Now can you guess what information would this give us? It is like the rate of change of the rate of change. This might give us an idea of how the steepness itself changes or how the function curves. If the function curves sharply near a point, then the second derivative is high, and if it curves gradually near a point, then the second derivative is low. Now we know what derivatives mean. They give us information about how a function changes near a point. The only thing left to do is to take all this information and put it all together. And a polynomial is used for this purpose mainly because they're easier to deal with than other functions. Here C0, C1, C2 are free to change and can be substituted for any number. Now for this approximation to be any good at all, the function and the polynomial should be equal at least at a single point, say x equal to 0. And when we input x equal to 0, we get that C0 and the function are equal at that point. Now if we took the first derivative of both the function and the polynomial and do the math, we get that C1 is proportional to the first derivative. That is, the slopes at x equal to 0 are equal. Similarly, if we took the second derivative of both the function and the polynomial, we get that C2 is proportional to the second derivative. That is, both the function and the polynomial curve similarly near 0. So if we add more and more terms, we get a better and better approximation, at least in some cases. This gives us the insight that when a problem seems too difficult to solve, there's always a way to approximate the answer. Thanks for watching.